Hey guys, welcome to another video. Today, another video in the final question series that I've been doing. So today's question comes from the Extension 2 syllabus from Hornsby Girls 2022 trial paper. Now, today's question is in the topic of vectors. The question is actually quite nice. It's a little bit difficult. I mean, that's what you would expect from the last question of a 4-unit paper. So let's see. Right. So before I dive in, as always, guys, if you haven't already done so, please subscribe to the channel, tell your friends, and like the video. Let's start. So let's have a read of the final question. Now, it's quite a lot of marks. It's about 7 marks in the question. So let's see what we got here. So, okay, I've got 2 lines, two vector equational lines, 1 and 2. Okay, pretty straightforward. Show that they intersect and are perpendicular. And are perpendicular, right? So let's see. So dot products 0. Is that right? Yeah. Of the so whenever you do direction, anything to do with direction, use a direction vector, right? And if you prove that direction vectors are perpendicular, then the lines themselves are naturally perpendicular. Okay, cool. Actually, I'll do that in green. Yeah. So that's what I have to prove. And state the coordinates of point. Okay. Point of intersection. Okay. Classic. The use of the plane has equation. Okay, so I'm going to prove that has this equation and hence show that the plane has this equation. Okay. And then lastly, perpendicular distance from origin. Okay. All right, let's work through this one at a time, right? So first part 1. Yeah, perpendicular. So obviously I'll be showing that they intersect, right? And not skew. So, and then find the point of intersection. So maybe I'll solve it simultaneously first. Find the point of intersection, and then I'll prove that they're perpendicular, right? In that order. So first one. So for R1, right, I'll set the X values, Y values, and Z values equal to each other, right? So it's plus 2 lambda equals to -1 plus mu, right? So set the sort of X values, that times that, right? Equals to that plus that times that, right? So equation number 1, 2 minus lambda equals to 1 plus mu -1 plus lambda equals to 0, right? So it's just negative mu. I'm going to solve that simultaneously, right? And show that there is a point of intersection. So maybe what equation number 1, 2, 3. Yeah. Maybe go 1 minus 2. Just to solve for that. So if I minus, I get 1 plus 3 lambda minus 2. That's gone. So minus 3 lambda equals -1. Right. And if that's the case, mu would equal to, so if I sub mu into, so sort of lambda -1 there, that's 3. 1 times 2. Let me just quickly check that. Yep. Okay. So I got that. Right. Now sub that. Sub into 3 to test, right? So then the left-hand side equals to -1, -1, -2. Right-hand side equals to -2. Therefore, point of intersection is, so I'll sub either lambda or mu into one of those equations. Maybe I'll sub mu in because it looks simpler, right? So intersection would be -1, 1, 0 plus 2 times 1, 1, -1. What's that, guys? -1 plus that's 1, 3, -2. Yeah. So therefore, POI, point of intersection, equals to 1, 3, -2. All right. That's 1 mark. No, so 2 marks probably out of the 3. Right now, I've got to prove that they're perpendicular as well. So now, so I'll do dot products of the two direction vectors. So let's see, what's the first direction? 2, -1, 1. 2, -1, 1. Dot 1, 1, -1. 1, 1, -1 equals 2. What's that? 2 times 1 plus -1 times 1 plus 1 times -1, which equals 0. So therefore, L1, let's go down a bit more. Therefore, L1 and L2 are perpendicular. Okay, guys, that wasn't hard, right? That's very textbook actually, right? The question on part 1, nothing to, nothing to write home to your mum, but right, really straightforward piece of work there. Now, the second part here is a bit technical, right? So needs a bit of explanation. So deduce that the plane containing the two lines, so picture two lines in three-dimensional space, right? I want to show that that plane has that equation, and then when I solve that, solve A and B, I get y plus z equals 1. Okay, now, the best way for me to illustrate this, right, and actually part of your answer for part 1 is, can you picture, if I have 2 points in space, right, and there's a vector equation, right, vector equation from a, so imagine a three-dimensional space, right? So let me try to illustrate this with a diagram. Okay. Yep. So imagine three-dimensional space where I have a vector I have, let's go, a vector equation going this way, right? And a vector equation going this way. Yeah. Now, if I say this is now what direction vector is it? 2, 1. So let's say this one here was some sort of parameter 2, -1, 1. Right? That's my, oh, let me call it direction vector. Let's go D1 equals that. Yeah, D1 equals that. And let's go 1, 1, -1. Let's go direction vector 2 equals to B times, what was it? 1, 1, -1. 1, 1, -1. Right? So I've got two direction vectors now. What that means is that envisage that these vectors can go long and short, right? So if I add them, right? If I put them together, so if I go and put this vector, right? Sort of like together, right? If I add the two vectors, right? It'll give me the whole plane, right? Basically, now how do I illustrate this? Let's go like this. Oh, give me the entire plane, right? Yeah, if I added, because A and B can move, right? A and B can be longer and shorter. And if I keep adding it, right, depending on what A and B, it'll basically cover the whole two-dimensional plane in space now. Yeah, is that okay? Now, but what that means is that I can have multiple, this three-dimensional space, right, can be anywhere, right, vertically, right now. So just to illustrate, it can be anywhere vertically, right? I can move it up and down, right? Whole plane can be moving up and down. However, right, if I know that the plane passes through a particular coordinate in space, a particular vector in space, right, then it's fixed. That's the plane that I want to find for this, right? So if I do a linear combination between the direction vectors of D1 and D2, and then I add it again to this three-dimensional space here, which is the point of intersection, right? If I add it to the point of intersection between L1 and L2, then that plane has to be where L1 and L2 exist, right? So this vector here, what was the answer for part 1? Hardly. 1, 3, -2, right? So if I say that this plane here was 1, 3, -2, right? So I'm adding the plane to a particular vector, right? So then it has to sit on top of that vector, and that's my plane where L1 and L2 exist. Does that make sense? Because right now, L1 and L2 is the pink plane, right? But it can move, right? Yeah, so if I just use the direction vectors of L1 and L2, it's the pink. But if I add it to the point of intersection, then it has to go through, that's L1 and L2, right? So my answer, really, the first part is the linear combination of 1, 3, 2, A, 2 minus 1, 1, and B, 1, 1, negative 1, will form the plane of which L1 and L2. Now, what word did I use? Exists. Therefore, right, they've defined x, y, z, right? So x, y, z is some point that lies on this plane. X, y, z, right, is a point that lies on that plane equals to the linear combination of 1, 3, negative 2 plus A, 2, negative 1, 1 plus B, 1, 1, negative 1. Yeah, does that make sense? Because basically, the two pinks, right, have a plane that moves, and if I add it to the green point, right, it's fixed. That's my plane where L1 and L2 exist, right? Now, once you get that algebraically, right, you got, if I equate the x's, right, I've got x equals to 1 plus 2a plus b. I've got y equals to 3 minus a plus b. And I've got z equals to minus 2 plus a minus b. Now, you can sort of see here, right, that if these are my three equations, right, and I'm actually cheating a little because I know that in the question that they're asking me for, right, y plus z. So I'm hoping that if I plus y and z right now, you can see that the a's cancel out and the b's cancel out. So if I go 2 plus 3, right, y plus, therefore, y plus z equals to 1. And that's my plane. Yeah, that's the equation of the plane. So pretty straightforward, right? So, and this, so you can actually then label equation of plane. Yeah. So the explanation for why we're doing this is hard to visualize, right? But the linear combination of those two pink direction vectors gives me planes that are parallel, right? And then you basically add in the point of intersection of where the two lines meet. That then says, okay, that's my only plane that exists where L1 and L2. So that's my only plane where L1 and L2 exists, right? Boom. Guys, last question now. If I sort of did the same as what I did just then, and I wonder how successful I could do this. Do that. Let me get rid of this. I'm just gonna move this up. Right? Let's say I'm up here, right? It wants the, now obviously it's not, I'm not doing it to scale here, right? But it wants the shortest distance. Now I'll do it off, just, I know that's not where it's supposed to be, right? But let's say I do the shortest distance there, right? Shortest distance there. Now, guys, I know that the shortest distance is always perpendicular distance, right? Yeah. So this is how I'm going to do it. I'm going to let the coordinate of intersection there, let that coordinate there be x, y, z. Yeah. Let it be x, y, z. Well, I know. Let the point be p, right? Yeah. X, y, z. I'll start there. So part 3. Let p, x, y, z lie on the plane. Now, since in this case, let's see, z equals to 1 minus y, right? From 1, so i.e. coordinate is x, y, and 1 minus y, right? 1 minus y. Now, if I wanted to find an expression for the distance, right, of OP, right? OP, let's go magnitude. Right? Therefore, magnitude of OP. Let's do OP squared, right? Because I want to get rid of square root, right? OP squared, so it's Pythagoras x squared plus y squared plus 1 minus y squared, right? Yeah. Now, with that in mind, let's see. Okay. I need to find the minimum value for this, right? Minimum value. Now, I'm thinking maybe let me expand this, right? Expand this. Let's see. What do I get? Plus 1 minus 2y squared. Oops. I'm going to complete the square here. So if I got x squared plus, let's go factorize the 2 out. I'll leave the 1 outside now. No, yeah, I'll leave the 1 outside. So I get y squared minus y. And I'll leave a space strategically, right? Because I'm going to complete the square. So let's see what I get. Let's see what I get. I'm going to add half of that, so add quarter minus a quarter. Right, so that gives me, let's see, plus 2 y minus a half squared minus a quarter plus 1. If I expand that, x squared 2 times this minus a half plus that's plus a half. All right, now this is cool. This is cool because what do I want? I want because the perpendicular distance, right? That's what perpendicular distance is always. Now maybe I'll say it like this, right? If I say that this guy here is a perpendicular distance. Oh, no. Maybe I'll just write it because that's just distance, right? So distance between origin and plane. Now, perpendicular distance, right, is equal to the smallest distance, right? Between smallest distance. Maybe, no, just write smallest. It's already defined as smallest OP, right? Does that make sense? So if I want the smallest value, right, you look at this expression here. Yeah, how do I make this the smallest? Well, I know if this expression is something squared plus half, then those two square numbers, the smallest value they can be is 0, right? So for example, right, when x equals 0, say, when x equals 0, and when y equals to a half, and both of these guys will be 0. So the smallest value this expression can take is basically a half, right? So let me put that into, I just need a little bit more space. Sorry. A little bit more space to illustrate this. I'm just going to move this up gently. Perfect. That's enough. Okay. So the smallest value this can take, right, is that. So therefore, smallest OP squared is equal to a half when x equals to 0 and y equals to a half. Therefore, perpendicular distance, I need a square root, all right, equals to 1 over 2. Is that okay? Wow, that's a nice question, right? So, guys, so this question started with solving simultaneously. I mean, that's textbook. Part A is textbook. Part B is important, right? Basically to say, right, that the linear combinations of two direction vectors gives us multiple planes, right? Infinite planes. But then if I add it to the point of intersection between the two lines, right, it gives me the exact plane of which the two lines exist. And then part 3, perpendicular distance, guys. Find expression for distance. in which case I sort of complete the squares to get 2 squares plus a half. If the 2 squares are there, the smallest value you can take at 0, so get rid of them, and the smallest value is half. If you like that, as always, guys, like the video, subscribe to the channel, and tell your friends. I'll see you in the next one. Thank you.